Okay, guys. Before we proceed with the way to calculate it, just a little bit of discussion on why do you need to know the formula and why do you need to know how to calculate eigenvector and eigenvalue. Why don't we just use a graph just like what I did before, right? We can still try to figure out the straight line from the original line just by looking at the graph, right? Right, if you look at this, we can just try to figure out, let's say we have this as an original line. We can just go, okay, so where it should be. So we can just try to figure it out graphically. But why don't we do that, right? Because of, right, you in real world, we usually encounter with a lot of dimension, right? We don't really just have, like our example, x and y, right? 2 dimensions. If that's 2 dimensions, actually, even if it's 2 dimensions, there's a lot of possibility of how can I say this, a metric, a vector that can become the vector for the eigenvector for our metric, right? If you just look at this, right, any value along this line can be considered as the eigenvector, can be considered as a vector for our metric just now, right? So if you just want to look at it, not just by looking at it through the graph, you might be having a hard time looking at it. So, and to make it worse, usually we are dealing with a real thing that has actually more than 2 dimensions. For example, you can just try to look at this. Okay, this object here. This is just just look at it and you'll see how many. Yes, just look at the dimension there. You'll see this is a vector, right? And it has a lot of dimension, right? That creating that object. Okay, so just imagine that we maybe we want to recreate this thing. Maybe we want to improve it a bit. Maybe we want to expand this area here longer, right? Let's say that's what we're going to do. And we know that this is the vector. So the idea is to expand maybe this 5 vector, right? But we need to make sure that they are expanding on the same line so that it will be straight up ahead, right? We need to make sure that. So basically, if we don't calculate it, we don't really know where is the estimated destination or the location that is in the same line. That is among the purpose of knowing the eigenvector and eigenvalue. Okay, so let's proceed with the calculation. Okay, let me set it up first. Okay, let's be clear a bit on what is eigenvalue and what is eigenvector based on our previous example. Okay, now we know that, right? Based on previous discussion, okay, this vector, when being multiplied with our matrix, will give us an expansion of a line without rotating, without changing to other direction. So if we try to just multiply it like this is what you get. 624. This is the final, this is the coordinate, right? This is the coordinate for after you multiply this matrix with the vector. So you can see here it is 6 and 24. So where is the eigenvector and where is the eigenvalue? Okay, so we know that this is the eigenvector. So how do we actually find out the eigenvalue? So we can find it out by finding the length, right, just by try to simplify this with respect to this vector. So we know that this is the vector that is that when being multiplied will expand the line but still remain on the same original line, and the value that we need to multiply with this vector to get this is 6, right? So 6 times with 1 you'll get 6, 6 times with 4 you'll get this, you get 24. So basically this 4 here is the x or the eigenvector, and this 6 here is the eigenvalue, right? Graphically we can say that this 6 represent this length, which also indicate that this line is 6 times longer than the original line, right? So this is what is eigenvector and eigenvalue is, right? So let's try to do the real our example, right, which is not 2 by 2. We are going to do 3 by 3. Okay, basically this is the formula that we're going to use as we discussed before. Now, right, I will input the question. Okay guys, please refer to question 1 Roman exercise 2.22. Okay, so they give us this metric, okay, and they want us to find the eigenvalue and eigenvectors. Okay, so by using this, we already passed through this already, discussing on how we can get how can we come to this formula. You can refer to the previous video. Now we're going to just use it, right? So this is the A minus lambda I. So basically this lambda will be multiplied with identity, hence it will become like this, right? And this is our x. Okay, so I just input everything in our formula. We have A minus lambda times I, okay, which is this, and then x equal to 0. Right, next what I did is just subtract between these two. So 1 minus lambda will give us 1 minus lambda, 2 minus 0, 2, 0 minus 0, 0. Basically the one that we're going to change is just the diagonal line here, because everything else is 0, right? So this is what I get after subtracting between A and lambda. Okay, right, for everything else we just copy it again. Now we want to find out what is the lambda. Okay, remember the lambda is the eigenvalue. You want to know the eigenvalue. Okay, what is the eigenvalue? So one operation that we can do is determinant, right? Because as we discussed before, these two, when we subtract, right, it is inverse, can't be inverse. So one of the property of metric that can't be inverse is that determinant equal to 0. I tried to refer to our previous videos on inverse, right? One of the properties of a metric that can't be inverse is determinant equal to 0. So this is the notation for us to conduct determinant. So find determinant for this, right, assuming that it will be equal to 0. So there is several ways that you can do. Remember what I did just now is just cross multiply it. Okay, so I cross multiply this, right? I cross multiply with this, right? So basically 1 minus lambda times this, right? This is it, plus with 2 times 1 times 3 times 1 lambda, sorry, okay, negative 1 times 2 times 0, which is 0, and then 2 times 1 times 3, which is 6. The way to find the determinant, please refer it back. You can do it this way, or you can also do it through cofactor. Either way is okay. So this is what I did, and then I simplify the calculation. Right, you can try to look at it, and finally I come out to this, the most simplified version of this calculation of determinant. Now when it comes out to this, we can find out the value of each lambda. So I get lambda equal to 1, lambda equal to -1, lambda equal to -2. Basically, there are three possibilities of eigenvalue. Okay, the next thing to do is to substitute. Okay, we are going to substitute our original formula that contain 1 minus lambda and everything just now with lambda 1. So when you substitute, you should get this. Okay, so just a little reminder, the substitution should be on this, right? Remember, this is what we did, right? Based on this formula, right? Based on this formula, and then when it comes to this, right? We already find out the value of lambda. We get 3, 1, -1, and -2, and we just substitute it back into this, right? To get to solve for x later. So when you solve for this, there will be no more unknown value in our matrix, and we can solve for the x, right? That's what we're going to do after this. Now we have 3 lambda, so lambda 1, just solve it like we did before using Gaussian. Okay, and one thing that I want to emphasize is this: we haven't used this kind of way before, which is switching between row. Right? This way is actually useful to be used if you encounter with a diagonal that is 0. So when we switch it, we will actually able to avoid the diagonal from it to become 0, because from 0 to become 1, right, to calculate it to become 1 is actually not easy. So by switching it, we have moved the 0 from the diagonal part where we need to make it 1 later, right? So I have moved it like this, and then I just calculate it as usual, and finally I get this as my final answer in Gaussian. So you can try to do it, and you'll see that when after I solve it like this, I change it back into linear equation. So I have x1 to x2 and negative x3. I just copy it back like this. And for the second row here, I have x2 equal to 0. But then I don't have x3, right? I don't have x3. So what I did here is I'll just put x3 as as a symbol, right? S, right? So when I put this as S, I can substitute it in our original formula to obtain x1, because currently I have x2 as 0, I have x3 S, but I don't have x1. So I will substitute this into our formula, into the first equation to obtain x1. So finally, this is what I get. So x1 is equal to S, right? When you substitute, you get x1 equal to S. I just input it here as x1x, x2 0, x3 S, and when I try to try to obtain the value with the eigenvector. Remember, I need to factorize it out, right? So when I factorize it out, I get this. This is the eigenvector, and this is the eigenvalue. So in other words, eigenvalue can be any value that being multiplied with this vector. Okay, we are going to go through several other questions after this, so that you have more strength in calculating for eigenvalue and eigenvector. Thank you.